this webinar. I will try to introduce you to the new model-based line differential protection, which we're going to put on the market in version 2.7 of the 670 series. As Marco said, it will be available in customized RED670. And we'll start with short introduction, why we have this, just some history. When we talk about line differential protection, then we assume that we are measuring the currents on the two sides of the protected line, and then typically that type of differential protection is then based on the first Kirchhoff law, and practically first Kirchhoff law says that sums of the current entering and leaving the protection zone is zero. And what that means, if we draw it then back in the phasor diagram, if we have external fault condition or full load condition, then we expect that two phasors measured on the two sides are 180 degrees out of phase, equal magnitude, therefore their sum will be zero, or differential current will be zero. And if we get internal fault that one of the phasors will turn around, they might have different magnitudes, but they will be roughly in phase. We'll have a lot of differential current, and then we can trip. However, the problem is that people starting to build quite in a new way, or new types of the transmission corridors or paths. Therefore, we have installations of the RED670 where actually you can see the recorded full load conditions. And if you just look into the local phase L3 and remote phase L3, which we record, and I just presented using the ComTrade viewer, we can see particularly that currents have different magnitudes and they are not 180 degrees out of phase. In this particular case, for this particular load conditions, we get about 100 amp difference and 15 degrees shift from 180 degree ideal line. And when we do some math, we can see that differential current then becomes around 200 amps, which is roughly 1/4 of the bias. And then the question comes, what is the problem? Why we have this, and what can cause? Because this as well might look like asymmetry, because we might say that this phase shift is caused by asymmetry between the communication channel, but actually this is not the reason here. And what is interesting as well to notice that this phase differential current is both voltage dependent and load dependent. Therefore, if the load for the line is changing or the voltage on the line is changing, the phase differential current will have different magnitudes. Actually, what this is installation of RED670 on the export cable. This is cables which connect a offshore wind farm to the grid. And the problem becomes obvious when you realize this is actually 100 kilometers of 220 kV cable. Therefore, we have extremely long cable. And then on the cable directly, we have connected variable shunt reactor. And here I have just pictures showing roughly what equipment we talk about. Here we have the variable shunt reactor. It's practically almost the same size as the transformer of roughly 200-300 MVA. And then we have the power cable, 100 kilometers. And what is the problem here? This cable, extremely long, has a charging current of about 900 amp primary. And this is quite a lot because the CT ratio here is 1500 to 1. And practically we have almost 2/3 of the ratage of the CT is just a charging current. Therefore, they try to compensate with this variable shunt reactor shown here. And this particularly introduces presence of both shunt capacitance of the cable and then shunt inductance of the variable shunt reactor within the protection zone. And this is quite new, or new ways how people build these corridors. And then at the beginning, we approach with RED670, where we connect all currents and voltages on both sides in order to try to do some type of compensation, because what is the problem here? Charging currents are huge. And the question is, can we do some of the existing charging current? And actually it has been shown it's quite difficult, because especially this variable shunt reactor is causing a trouble because it's changing most of the time, varying the level of phase differential current. As well, they want to have common setting even for contingency operation. That means when the reactor is out of service, because they as well can, by some disconnectors or manually, remove this variable reactor out of the service. In that case, we just have a cable and they have common settings and so on during the operation of the device. If you read some publication, there is people who claim that, some of our competitors who claim that if you connect this CT here to the line differential protection, then you can use the standard charging current compensation. But even this doesn't work. And I'll show you on the next slide why it doesn't work, because when you energize such complex object, combination of long cable and reactor, first the currents are not really at the beginning 50 Hertz, you can see it here, then something causes a trip here, doesn't matter what. But what is important to understand, you have huge current and voltages, even if the primary breaker open. Therefore, what I want to say, we have energized line here, then we open this breaker to trip of some device. We still measure quite a large current at this point, even bigger than bells during energization. You can clearly see here, this is the shunt reactor currents. As well, frequency is very strange. It's not 50 Hertz. It actually depends on the present L and C in the circuit, where C is constant of the cable and L is variable because the shunt reactor can be on different taps. Therefore, first conclusion is that we have the post-fault oscillation or post-breaker opening oscillations, which can be of different frequencies. And this actually is the main reason why we do not recommend to actually include the reactor current into the protected zone, because it just causes you trouble. And it's almost impossible not to mal-operate here, both for distance protection and for the line differential if they have connected these measurements of the protection. Therefore, the main, as well, what we learned here, that we should not include this reactor current to line differential and to distance protection. You may do it when the reactor is small, but when the reactor is big, 300 MVAR, and you have huge capacitance, this is practically then mission impossible. Okay, then what practically the customer or we've been forced to do in this installation, that we need to raise the pickup. And in this particular case, the pickup need, it was almost at 250% of the CT rating in order to cope with all phenomenon and not to cause maloperations during normal operation of the cable. And of course, this is not ideal situation, because sometimes this might cause a problem that we don't see some internal faults, because pickup is roughly about 2 kiloamp primary. Of differential protection. Yes.
Zoran, could I interrupt? Sorry. One question. So, what is the application check that is required to support that this functionality is required? Is it the capacitance of the export cable and the reactance or the inductor?
It's their combination, because you don't have really fixed. You don't really have fixed protected object. It's sort of moving, because this reactor has about 25 taps and has very large variation, practically 50% variation from 150 MVAR to 300 MVAR. Due to different reasons, they will typically start energized cable with relatively small 150 MVAR reactance, and then they will tap up in order to compensate for the charging current. Plus, once you start to loading the cable, they'll have to tap the reactor up and down in order to find the optimal point. Therefore, we have variable conditions, and it's very difficult to sort of see in advance all operating scenarios. Plus, they can, under emergency situations, they might even remove the reactor or during commissioning phase. And what is a little bit special for the wind farms, commissioning phase can be months, even 1 year to 2 years to finish the commissioning, because you're dependent on the weather. It's very harsh environment. What is very specific here, commissioning phase can be very long, and during some parts of commissioning phase, maybe cable is energized, but reactor is still not delivered, and they will have different operating scenarios which they need to cover.
And this is then applicable for very long lines in some way with big capacitive contribution, right?
Yeah, I'll come to that where we can use this. This is just sort of the story why we have developed this.
Okay. A follow-up question. In that case, what about short cables? If it's only 30 kilometers or 40 kilometers, do we still require this
that's
function?
already not really short cable, but yeah, cable a couple of kilometers probably not problem, but as soon as you say it's 20-30 kilometers, yeah, you can start to consider this one. Depends a little bit as well on your available short circuit level. If you have very strong system where you connect the currents are high, then you probably can live with a normal differential. If you have relatively weak system, your fault or under some conditions in the system you have relatively weak system and you need sensitive pickup, then classical differential will run into trouble. Therefore, it depends on the not only on the cable but where you install that cable.
But Zoran, okay, maybe I'm not an expert, and it's also a question which is not correct. Thing is, how do from the technical and how do we promote this, on what basis we go to
But
the
we'll
customer
come to
and say,
that.
look, okay, thank you.
We'll come to that. I'm just trying to explain why we have done this, because
thank you.
in this particular customer, who is Ørsted, was not really happy with the setting which we had to put. And they have other manufacturers as well. They have bought protection from other people. And this what I said regarding post-fault oscillation. They had problems with other people as well who mal-operated in case when the reactor current was connected. Therefore, now their standard practice in Ørsted is not to connect the reactor current to neither line differential, neither to line distance, because it just causes trouble when you open the breaker. And if you read some of our competitors, they would say, oh, yeah, but it's not problem. Breaker is already open. But of course, for the operational people, it's nightmare because you open the breaker and suddenly you get several hundreds of trips. Everyone get confused.
Just a quick question. The voltage, the VT was connected during this time or not?
Yeah, VT you have here.
Okay. Yeah, I missed that. Yeah, thank you.
You have VT and you have what current are shown here. The first current is current here. The second current is current of the reactor. The third trace is the voltages here. Therefore, you have 1, 2, 3, and that's shown here, 1, 2, and 3. And what is the problem? Once you energize the cable, you store the energy in the cable capacitance. Once you open this main breaker, you have stored energy and you have almost no resistance. Therefore, this will start to oscillate. You'll have LC oscillation, which will last there for quite long time. And during this time, all protection which measure these signals will sooner or later go crazy. Therefore, it's very difficult, and the frequency is varying because it's dependent what is the tap position at the moment of breaker opening on the shunt reactor. Therefore, yeah, they are not using anymore the reactor current. Particularly, they want protection scheme which just measures here and there and provide the protection for the cable. Okay, then what was the possible solution? So-called two-port circuit theory, also known as ABCD modeling, is used for quite a long time, and this practically provides metrics relationship between current and voltage on one side of that object and on the other side of this object. And this theory is known for quite some times, more than 50 years. This is a book published in 1960, which describes this, even used in the power system, how this can be used in power system. How we can use it in power system, because we have three phase, we actually can use it for every sequence. Every sequence quantity or every component can be in the sequence domain, positive, negative, and zero sequence be represented as these two-port systems or ABCD matrices. How we can use it for shunt reactors? Again, this is well-known theory. Many simulation software today, which runs for example, PSSC and this type of steady state simulation software, which runs on phasers, are very often using this methodology to simulate the power system. And then the shunt reactor with the neutral reactor can be represented in this way. little bit of mathematics, but unfortunately we cannot avoid it. Then what is the problem? If this becomes variable, then we actually need new metrics for every tap position. Therefore, we come into similar situation to do on-load tap position reading and compensation, but that's in principle nothing new. We do this last 30 years for the transformer differential protection. Therefore, now we'll introduce this into this model baseline differential as well. When you have variable shunt reactor, we would need oscillator to read the position and compensate for it. But once more, it's nothing extremely new, this compensation, because we're already using very similar principle for the transformer differential protection. How we represent the line, because we have cables, we actually have decided to use the most complex model of the line, which is the using cosine hyperbolic or sine hyperbolic. This might look very complicated, but in principle just boil to two matrices with 4 elements each. Because for the line differential, we need the model for the whole length. That means this x is 100%, and then you just calculate values for A, B, C, and D. And in this case, actually A and D are exactly the same. What is the line section? Can be section of the overhead line or section of power cable. What is give us advantage if you have mixed line? If you have combination of overhead line and cables, we can model every individual section, and then you'll see later with help of that we can model the whole line. How we can measure, how we can model series impedances as well. We have series compensation capacitance, but now in many countries they as well start to install the series reactors, and both of these as well can be modeled in a relatively easy way as shown here. Therefore, all what we need to do is just to know the impedance of that either capacitor or reactor. Of course, X will be positive here and will be negative for the capacitor, but that's what you need to enter as a setting. Therefore, we can represent these individual parts of the protected transmission path with relatively simple matrices. One good properties of this ABCD approach is that when you have cascading connection, as we have shunt reactor, then we have a cable, then maybe we have overhead line, you'll see later in an example. You can represent the overall model for the whole system by simply matrix multiplication of individual elements. Therefore, if I have 5 elements and I have 5 matrices, one for each of these elements, I simply can just multiply all of them and get overall model for the whole system. What I want to say, if I have this mixed line, when I have 2 cable sections and 1 overhead line section, even what we have today, this voltage-based charging current compensation cannot properly compensate for this because it has assumption that capacitance and inductance are uniformly distributed along the whole line length. Here you have 3 distinct sections. These cables might have different constructions. And of course, your capacitance and inductance will vary between these 3 sections. With this modeling, we can model every of these sections. We particularly use 3 line section models, and then we can calculate the overall model by multiplying individual matrices one by one. What is important to understand? That depending on the complexity of this installation, metrics from left to right, overall metrics, and metrics from right to left might be different, but I will show you how we handle that. Then what is this model baseline differential protection? You see, we still have 2 IDs, like we have standard line differential protection. We measure local current and voltage. And then with help of these metrics for the whole protected object, we actually can estimate which currents need to go out. If I measure my local current and voltage, green one here, and based on this measurement and this overall metrics, I can very exactly predict which currents need to go out of my line on the other end. If I know this, then practically I can form the model-based differential protection, because model-based will be red current, estimated current, against the blue current, which I get receiving via LDCM. I have the next slide, a little bit more detailed calculation. But that is the basic principle. If I compare red against the blue, I get model-based differential protection. If I compare green against the blue, I have the classical differential protection. With model-based, I actually have 100% compensation. I compensate for everything on this transmission path. Therefore, ideally, I'm getting zero differential current, as you will see later. While I'm comparing this one against that one, then I really don't compensate for anything, and I might have, depending on the complexity of this protected transmission path, relatively large fails differential current. And what we're doing now in the line differential model based, we're actually running both of these two in parallel. Therefore, we have two parallel differential functions inside of this. We have classical one, the traditional one, and then we have the model based, which run in parallel. What we're achieving, classical one, customer will easier understand and easier accept the solution. The model-based one give us sensitivity. Particularly, we can say that model-based is like a sensitive addition to the classical line differential. And I'll try to explain that in further slides.
Zoran,
yes?
Zoran, one question again, sorry. So that means with the model-based line differential, the operation is supposed to be accurate, right? Or
the measurements operation cannot be accurate. The measurements can be accurate, yes. Okay. The measurement will be accurate, therefore you will see later on, I will show you, for example, you have this composited line, relatively complex, model-based measures zero differential current, while the classical one measures 10, 20, 30%, depending what all you have in the circuit.
Okay, that's so the measurement is accurate. Okay.
The measurement becomes accurate, therefore you can lower your pickup level.
Okay, thank you.
How measurement is done? We practically, from the measured current and voltages, use the sequence component, and based on sequence component, estimate what sequence component I should have on the other end of this circuit. Of course, I need to know this overall metrics. I'll explain that how we do it in some coming slides. Once I know the sequence components with this relatively simple mathematics, I can estimate the remote current per phase. Okay. And then if I estimate this remote current, I can form my differential model based by comparing this against the current I'm receiving via LDCM. All this mathematics I do here. I get the estimated current, what needs to leave on the other side. I get the measurement from the remote side via LDCM, and then I form the model-based differential current, summing estimated what needs to go out against what I'm getting via LDCM. And if everything I do properly, I practically get zero here. And you will see later on, regardless how complex that thing is, I still measuring zero differential current because I compensate for all capacitances, all inductances, all resistances, whatever I have on the path. And what is most important, that works irrespective of the voltage level and what my load is, because I compensate that automatically. Therefore, during different and varying conditions on the line, I'm still measuring zero differential current until something happens, I get internal fault, then I can trip sensitively. And of course, the other ID do exactly the same calculation, but just in opposite direction. And I'll explain that in the coming slide. These overall matrices might be different in this ID and that ID. But we have the way, yes?
So, one question, this IA model differential A primary, is this the current on the left side or on the right side?
You see, you measure the local current. From the local current and local voltage, and using these metrics, you actually calculate what need to go out. Based on my measurement and the properties of what I protect, this current need to go out.
That is
that's my estimation. And then I compare my estimation against the current I'm getting from the other side via LDCM.
So this is all happening in the left bus eye.
Yeah, this is all happening in the left bus eye. This one estimate this current, receive this current via LDCM, sums them, and get the model-based differential. The other ID do exactly the same. Based on its own measurement, on its own matrix, estimate current here, this estimate current sum now with that current which you're getting via LDCM and calculate the model based on the right-hand side.
Understood,
Okay?
yeah. Thank you.
What that mean in the phasor domain? As I explained you previously, when we now measure the currents, my local current and my remote current will have different magnitudes and will not be 180 degree. Once I apply this calculation, I will move my local current to be exactly 180 degree of the remote current and exactly the same magnitude. Therefore, I will compensate both for, you can say, magnitude wrong and phase angle wrong doing by doing this modeling. And then I practically pull back what I measure to be exactly opposite what I measure from the remote side. That sort of, I'm not sure does it help you to visualize, but I'm measuring this remote, this local current, then I compensate my local current to estimate what really need to go out on the other side, and then I sum my estimate with what I measure from the remote end, and that's then 0 because I do proper estimation, I do proper compensation for everything I have from between two CTs. Okay? Now, what is important to understand that now within this model baseline differential, this is the logical name or function name, we actually running two algorithms in parallel. We run model-based differential feature and we run the classic differential. Classic differential, that's simple, local current plus remote current. Of course, that will not be ideal. I will have relatively large phase differential current, but that's what customers are used to today to have. In addition to this, in parallel, we as well run the model-based differential. And once more, in the model-based, I estimate what shall go out on the other side, and I deduct that from what I'm actually measuring via LDCM. If I do my estimate correct, this sum is 0. This sum is not 0. That depends on my capacitance, on my reactances, on voltage level, and depends on the load level. While here, I compensate for everything and measure the 0 differential current all the time, except I have internal fault. What is the idea with this? This one now become practically phase segregated sensitive line differential protection. We've been testing now this in RTDS. We can trip for internal fault resistance of 500 ohm, 600 ohm, depends a little bit on the setting. For with this one, we can detect really high impedance fault, phase segregated. We only trip the faulty phase. If customer want, we even can do single pole auto reclosing if needed. Of course, not on a cable, but if it is, for example, series compensated long overhead line, we can do no problem single pole auto reclosing for high impedance fault. Of course, what you pay here, you need a local VT measurement. Therefore, you are dependent on the VTs, not only on the current transformers, but as well on the VTs. Therefore, if you have VT failure, you need to block this. And you can do that in configuration because we have the fuse failure and we can block it. Okay. Here you have sort of comparison. Therefore, regarding charging current compensation, we have perfect charging current compensation here. Here we have no charging current compensation. This allowed us to set this sensitively and to set this relatively high, but this will cover the higher level faults. If we now look into the characteristic, what we now can achieve, we have two operational characteristics, one for the classic one, and remember, the customer was setting this to 150%, and now we introduce this model-based, but this one we can set much more sensitive, 25% and higher level to 75%. This 25% level, we need to slightly time delay, maybe 30, 40 milliseconds, but we are quite sensitive because my differential current, phase differential current can be almost 100%, and I'm setting it to 25 of that. 75%, we can trip practically instantaneously here without much time delay. Over 150%, the classical one will pick up and trip. Particularly what we're gaining with this, that sensitivity. And covering low-level faults, which might happen if you have weak system where you connect. How we have implemented this in IDs and tools now. This was a little bit of theory. Now how this is implemented in the tools. Let's say we have this setup and we have one variable shunt reactor, one overhead line section, one cable section. And this sometimes happen in the wind farm installation because on the shore you go by overhead line. Only when you come to the coast, you go to the undersea cable to the platform. Therefore, this can be as well offshore installation, for example. How we'll model this? We'll model it by one variable shunt reactor model, 1 and 2 line section models. And we have several models available. One is for variable shunt, one is for fixed shunt, one is for series impedance. Therefore, 3 different types of impedances, and then line section. Every type of function block, you have several instances. And then we have this matrix multiplicator. If you remember in this cascading connection, this one is actually providing this overall matrix from up to 7 individual elements. If you do matrix multiplication and provide single matrices to the line differential protection model based.
You have to put them in order, right? The elements.
Yes, I come to that. What is important here? You see here, I have, if I look from left bus to the right bus, I have variable reactor, I have overhead line section, and I have cable section. When I do my configuration, I need to put variable shunt reactor number 1, line section for overhead line number 2, line section for cable number 3. Whatever I don't use, I leave it not connected. That's very important. No group off, nothing. You just leave it not connected. And then inside of this, you have a setting which will calculate from 1 to 7 or from 7 to 1. Why we need it? We need it because we can have identical configuration and settings in both IDs, left and right. But in the left ID, we'll say calculate 1 to 7. And in the right-hand side, the ID will just say calculate 7 to 1. And then everything is done. We have everything identical, ACT, PST, except this one setting, which is different. In this way, we treat this, that matrices are different from different end. But hopefully engineering is relatively simple. What you need to understand, whoever buys this is unique engineering, which correspond to his power system. Therefore, if you would have additional reactor here, that reactor need to be represented here and connected as number 4. Okay? Therefore, you need to engineer your system in the way as it is primary system designed. Therefore, in that respect, we really cannot have the standard configuration because typically every installation is slightly different. Yes, please.
Okay, Zoran Nemanja is here. Is it thought about, it is focused now on line differential, but are there in practical some cases where you have some transformation in the zone of differential protection, like some auto transformer or some transformer?
Mm-hmm. Currently, we don't support transformer. Of course, this can be extended. But in present, today, what we release in 227, we can just support the line differential protection.
The idea of the model base is definitely something what can be adapted to be used for that.
Yeah, it can be extended, of course.
Yeah.
As well, what we have done in the PST, we have made separate model-based sort of section. If you are familiar with 670, we have current protection, voltage protection, differential protections, impedance protections. Now we have make new category, model-based protections, and all these function blocks will be practically lying there. Therefore, in the future, depending on market responses, so we can expand this. And I have presented this to some customers. They have some new ideas and some new things to how things can be handled, because currently we only can connect. We have only series connections. We have customers who has parallel cables here. They have 3 parallel cables here due to capacity. Currently, they have to model it as 1, but they would prefer that we model it as 3 separate. But currently in this version, we don't support that. Okay, that is as well some future improvements. Currently, we can connect up to 7. I have a slide on that. Up to 7 elements. That's as well the limit, because we have to put the limit on this here, how many matrices we can multiply one with each other, because all buffers and everything need to be of finite size. If you have variable shunt reactor as here, then you need to use this ELTC function block, and we already have them in transformer differential. We have just taken exactly the same one, which will then read the tap changer position, give the tap position here, and then we'll calculate for every position new matrix. What is important to notice, all these fixed, or more or less fixed impedances like fixed shunt reactor, fixed series impedance, and variable shunt reactor, they have out of service input. And when you energize it, we practically take away this out of from calculation automatically. In this way, you can dynamically take them in and out. Line section, currently you cannot take out of service because they are physically large over larger distance. Until now, I don't know any application where you can easily take away the line section out of service.
Soran,
Okay.
one question.
Yes.
We saw a situation where you had the variable shunt reactor on the line side. How does it work when you have the variable shunt reactor on the bus side?
Then you don't need it because then it's outside of the protected zone.
Okay.
You need to model whatever is, because my CT and VT are here and there, whatever is in between, I need to model. What sits here, I don't see it, it's outside.
Okay. And what about a fixed shunt reactor instead of a variable within the zone? This is also...
Yes, we do it in exactly the same way, except that we have another model for fixed shunt, and then you don't need the on-load tap changer because you could just, it's modeled in exactly the same way, but we have 4 different models: variable shunt, fixed shunt, fixed series impedance, and the line section. That's currently 4 elements we have.
Okay.
Every one you have several instances. Therefore, in total, you can build your 7-element installation, and then you can connect this to your model base. Therefore, I have a slide which is the limit. Limit is 7 elements.
Yeah. Okay.
I think I have this as well. Which data you need? You don't need any magic data. For the line section model, you need the line length. You need R1, X1, B1. These 2 you already need for the distance protection. B1 is just the admittance. You need R0, X0, and B0. And that's it what you need for the line section. Every line section need to have this data. And this is lump data. We'll then calculate per unit of length and do all calculation internally. For it's not, you don't need any magic data for variable shunt reactor. You just need to specify the impedances for low tap, mid tap, and high tap. That's typically is tap number 1, mid tap, and highest tap. And then you need to specify if you have the 4th reactor, because even there is installations where you have variable shunt reactor with a neutral reactor. We can handle that as well. If you don't have neutral reactor, you just put 0 and 0 here. And practically you remove the neutral reactor, 4th reactor from the calculation. Therefore, and this data you can find on the variable shunt reactor nameplate, rating plate. We do linear interpolation between here. It's not perfect, but it's good enough for all practical. Error is less than 1-2%. And you can slightly compensate here with this parameter. This is explained in the manual. I'll not go into details here. Therefore, between these 3 points, we do linear interpolation. We have these 3 points, and between these 2, for every tap, we do linear interpolation between the values. For the fixed reactor, you will just enter X. And for series impedance, you'll just enter R and X, and that's it. Okay, as well, we provide quite a lot of service values. Therefore, from this multics multiplicator, you will get all calculation available in the service tool, where you can see A1 parameters. All these matrix elements are complex values. We show them everything in per unit, That's maybe what I didn't mention. You everywhere have this global base. All these elements describing all this need to have common base. Base current and voltage need to be equal for all these elements here, all these function blocks, okay? It's very important because we use the per unit system, and these global base values are sort of base values for current and voltage to calculate everything in per unit system. As well, we provide the service values that for customer can see and can check what we calculate, because you can do all this maths in computer using Excel or any other tool. We'll as well looking into that to provide some Excel tool to calculate this in parallel that you can check. Regarding the application, this is, let's say, some typical application. Mixed lines, export cables, and you can have with variable shunt reactor or with fixed shunt reactors. We support the fourth reactor for all of them. If you don't have it, you'll just enter 0 and 0 for R and X value here. Here is probably the most complex what we can build, because here you have 1, 2, 3, 4, 5, 6, 7 elements. Therefore, that's the limit. This is very, very complex application with, and this even can be variable shunt reactor, but I still didn't see such installation. But this installation do exist with this complexity, and we can model it up to 7 elements. Any questions up to now?
I have a question.
Yes.
So the first few in the first, I forgot the slide number. We had this inductance and capacitance reacting to each other. When we take away this measurement from the reactor, do we overcome that issue, or how does model-based?
Because I only measure here and there. Once I open the breaker, I don't see this ringing current. Because I measure here and I measure there. When I open the breakers, ringing will be this way, and I will not see it because I will see on the VT, but there is very simple logic. As soon as we don't have any bias current, we kill the model based. Of course, we try to cover all these special conditions. You always need to do this in any function. Whenever you have some special operating condition, you need to know what to do.
Zoran, one question.
Yes.
When we have fault, how this on this slides when you show the blue, red, and green current, so how this red current then behaves? I mean, when you are pulling it through the matrix.
I have exactly now have some examples to show you.
Perfect. Okay. Okay.
Yeah, I'll come to that. It's particularly next section. Some test results.
Okay.
Because a lot of people think, look for internal faults. If the faults are heavier, both the model-based and the existing one will practically measure the same. Because here you can practically see calculation of the model-based, and you can see calculation of the existing line differential function. And this is relatively simple example, 266 kilometer long, 220 kV overhead line, okay? Which is quite long line. You still have some capacitance, okay? But what I want to show you is this one. After this fault, they do auto reclosing on this line. And you reclose breakers at different point of time. For example, in this particular case, the remote breaker close first, and then the local breaker close here. And you can see what this how we call it, simplified charging current compensation in RED670 does. It jumps to 22% of the diff current, and over the time learns it and then kills it. But you can see model based here. It can recognize even this site where I do measurement is not really breaker is closed, but I get voltages and I can estimate exactly what need to be out on the other side. And you can see that in the beginning, while the breaker is closing, I get maybe 6-7% of diff, but then it fails below 2%. and keeps there irrespective that you have energized the line and get the power flow and get everything. Therefore, it's quite, it seems to be extremely exact. I'll show you something when we're testing it in RTDS. Even people testing RTDS don't believe it's so good, but I'll show you. And if you get external fault, even our approximate charging current do some things because things are changing. You can see present line diff, and you can see that model-based diff calculate this is 2.4%, less than 3% diff current during this external fault. Regardless that current are jumping and you have all sequences involved and so on, it's not a big problem. Question which I get, what happened when you don't have really sine waveforms? Because I'm using just the phasors. You can see I have two examples here. This is now energization of this long cable with the reactor. Therefore, you have energization of this 100-kilometer cable. What does it mean? I only have current on one end and I have no current on the other end. Remote breaker is open. I have just closed the local breaker where the reactor sits on the shore. And you can see our present diff jumps to almost 40%. And you can see model-based, just during closing of the breaker, when all poles are not closed, it calculates a little bit of diff current and then settles down to less than 2%. Therefore, even all this energization and everything is handled in pretty good way. This is another example of this cable energized, and then you energize transformer on the other side. Then you can see that these currents are not really sinusoidal. But classic differential stays roughly on 12%. Model-based stays well below 4%. Just during here when this breaker is closing is slightly blip, but it's actually less than 0.5% here. During
a question here. When we are comparing the classic diff, did it have any compensation turned on?
No,
or
as I
just
told
the
you,
classic?
they have killed it because it was quite tricky.
Okay.
Due to variable. This is this cable, 100-kilometer cable with variable shunt reactor. When you energize the transformer on the other side of the cable, if you have cable in operation, when you energize another transformer on the platform.
Yeah, it's the pure differential current that's found in the classic
not pure difference. You
calculation.
have practically through inrush. You have inrush on the other side. Therefore, inrush is seen as load or through load condition. Therefore, you see that even the classic one stays on roughly on the same level, but model-based is not confused because here you don't have 50 hertz. Huh? You have a lot of harmonics because you're energizing relatively large transformer, but still all calculations are pretty good.
Mm-hmm. That's nice.
Because these currents, you can see they are not nice sine waves. This as well gives us more opportunities to actually supervise the communication link, and you will see on some coming slides some results. But if we do this perfect compensation, then these two phasors need to be 180 degrees out of each other. Magnitudes need to be the same. If they deviate from that, we can try to then estimate what is the asymmetry in the communication link. And this is something which is introduced, but we currently don't have any automatic blocking. We just have service values for asymmetry and for this angle, which need to be 180 degrees. And this is practically shown here. You can see here, for example, this is during testing in RTDS, when we have series composited line, and we have roughly 250-kilometer long line with two capacitors. But just first to show you, you see this angle is 180 degrees with very small error. And this was interesting. Model-based differential is practically zero. This is percent of the CT rating. Classic diff is about 11-12%. Bias is 80%. Therefore, we can fully compensate for everything on this series compensated line. Because you can see that model-based differential is practically zero. We as well provide the measurement of the remote voltage positive sequence. You can see remote we estimate from here that remote side is 99.35%. Currently, again, because it's line diff, we don't do anything with it, but you have the service values and you have value available in the ACT, therefore you can do the with logic and help of comparators, which we have in 227 and in previous version as well. You can do remote end over voltage protection, such things you can design and engineer in this ID for the remote end. Of course, what we need to realize that secondary injection now becomes a little bit more complex because people used to test differential protection with 1 amp in and 1 amp out. You really cannot test the model-based part in that way. You actually need to sit and calculate, and this is, for example, given some examples in the application manual, you need to inject both current and voltages in the left-hand side and right-hand side IDs, and all of them need to be properly calculated to see that differential current is, for example, 0. For this condition, your classic differential will be 16%, your bias will be 100%. But if you just inject random quantities, it will not be correct. We have some ideas on recommendations in the manual, but this is quite new. Therefore, Omicron as well doesn't know how to test it.
So Zoran, in short,
yes.
that means we need also the remote and relay to test the model-based
yes.
function,
yes,
even in the factory.
Preferably, yes.
Mm-hmm. Okay.
Look, you can inject everything locally with Omicron because you have inputs, you connect them yourself. But yeah, it's preferably to have that. You can, if you want, you can organize some testing, but then you need to make special configuration for that. Because then you need to, even the remote currents connect to the local Omicron.
Sorry, Georg here.
Yes?
Has Omicron tried it with relay test to run some tests on this?
No, I didn't try it to do it. We have run it on Omicron, on the RTDS, and we have played back quite a few actual contracts from Orsted installation on these long cables, but we did not try to run the Omicron.
Because customers are more and more using Omicron relay test. That
Yeah,
might be a good feature
that
to
can be
test
one possibility to test. Yes, that's probably a good idea. But of course, you need to have license for that as well. That doesn't
of course, it's not cheap. Yes.
We have RTDS here instead.
Yeah, of course, for you it's definitely, but looking at our project or installations at customer side then. Okay, thanks.
Yeah, some conclusion, particularly this is the maximum application, what we can cover. Therefore, we can cover 1.5 breaker on each side, 2 CTs on each side, VT. You need 2 megabit communication link. And via link, we just need to exchange the currents. Therefore, in principle, to operate, you don't need remote voltage. However, in 2 megabit communication link, you can transfer 9 signals. Therefore, you can transfer the voltages as well. And they are good because then we can, when we record everything, we can then verify the ABCD parameters, even calculate them. Therefore, remote voltages are not required, but it's good to have because then if any issue comes, we can quite easily calculate everything. Okay. It was a question for a short cable. Therefore, as you can see, the main installations are particularly more complex, long lines, long cables with shunt reactors with series compensation. If you apply this on a relatively short line, as a result, your ABCD metrics will be practically unit metrics, and your model-based diff will be equal to classic diff. Therefore, all what I want to say, for very short lines, you don't have any benefit using model-based differential, because your model-based differential and classic differential will be approximately the same. Difference will be 1-2%, while the biggest benefit is the long complex lines and cables, mixed lines, where you have varying parameters along the line length. We can accommodate up to 6 different line sections within one line. That's current limitations, what we have available as a function blocks. Once more, we as well calculate the remote end positive sequence voltage. Therefore, you can as well do remote end over voltage protection. But this needs to be done in the logic. We provide the values, you can record it, you have it available in the ACT, but triggers and time delays you need to engineer separately.
Just one thing to mention there. I saw that you mentioned LDCM in 2 megabit, and this works as well with the LDCE, the Ethernet based.
Yes. Yes, it works.
That is coming in
LDC
227
as well. Yeah, which is coming 227. Yeah, correct. Together with Ørsted, Itachi or myself has written the paper which will be published in SIGRE, which describe the issues for these export cables, not only for the line differential, but as well for distance and for directional air fault. It will be published in May this year, middle of May. And that's practically the first paper where we'll talk a little bit about some type of introduction, because Ørsted want to say that this is one possible improvements and one possible future way to protect such complex installations. As well, they are going to order, as far as I know, 36 IDs for the next project with this functionality, because they think it will benefit them in their projects. Therefore, I think what is the main message to our end customer, if they have need to protect complex transmission path, we have right solution for them. Limitations, once more, is 2 end objects, 1.5 breaker on each side, up to 7 individual elements within the protected zone. Thank you. Any questions?
Zoran, in respect to the CT saturation, the blocking will still be at both ends, but what happens when you need to send a signal to the other end that one of the CTs is saturated? Will the differential caused by that be faster than the actual signal sent by LDCM in this case?
No problem, because you need to wait for samples anyhow to come, because you will not run until you have all samples. But I just want to show you, we have a cut-off block level. This is a setting. Typically, we'll set it around 200%. Therefore, if your bias becomes bigger than 200%, then we practically automatically block the model-based. Because if the currents are high, you really don't need the model-based. Or you're having more risk that it will mal-operate. Therefore, we automatically block it. This is settable, but we recommend to set it between 200 and 300%. And this automatically take away the model-based, and the only classic one is an operation for the high currents condition.
Thanks.
Right.
Yeah, some more questions? I think I'm right on time.
Yeah, we are good with time, and thanks Zoran one more time for the presentation and answering the questions. And yeah, really happy. I mean, from my side to have this function in 227, and yeah, let's see then for the improvements as we go on with next releases and with next generation, of course. But this is the first step, very important one, and covering, I mean, so many use cases. So thanks.
Yeah, and just for you guys, practically we are the first company in the world who has model-based protection actually available. A lot of people, a lot of publications about it, but we are the first one actually to have it available to be sold commercially. And we need to, take advantage of this and practically speak with the end customer and tell them that we have solution to their complex problem.
Yeah, so now it's time to influence the customer specs. Show them the benefits.
I see
Alright.
that Hoda has raised hand.
No, thanks. He answered. That was question same as Sir.
Okay.
Good. All right. So let's then close, and we will, yeah, follow up on any, if anybody has any questions further on. So just reach out to us in GPG.